Hello everyone and welcome to virtual PQCrypto 2020. My name is Thomas Decru and I'll be presenting a paper called Seaside on the Surface, which is joint work with Wouter Castryck. I'll start with a brief introduction to sketch the background a bit, and even though it's an isogeny-based cryptographic protocol, the underlying mathematics are not too hard, so even if this is not the field you're very familiar with, it should be easy to follow. I think over half my slides are images anyway. Okay, so I'm guessing most people know what an elliptic curve is. Typically it's given by some form of equation, say a Weierstrass equation. We add a point at infinity and then we have a group operation as well. And an isogeny is a certain type of map between two different or same elliptic curves. It's a specific type of map, but we don't really need to know the exact definition. For this talk, the most thing that's important is that isogenies have a degree. Let's say the degree is n. Then we talk about an n-isogeny, and this in a way determines the complexity of the isogeny. If n is a large prime, it's going to be kind of hard to compute. However, if n is a large smooth integer, then it's a lot easier. Why? Because we can decompose an n-isogeny. If you have an isogeny of degree 6, you can decompose it as the concatenation of an isogeny of degree 2 and an isogeny of degree 3, which makes it a lot easier to compute. Now, how can you use isogenies in a cryptographic protocol? There's two main branches of cryptographic primitives based on isogenies. I'm going to give a quick sketch of Seaside on a toy example here. I'm going to represent it in a graph. So these 23 black dots represent elliptic curves over some field Fp, some prime field. All right, and now we're going to also use edges to represent the isogenies of degree 3. And if you do this for the isogenies of degree 3 over the ground field Fp, then you'll end up with a graph like this. Every elliptic curve over the ground field has two outgoing 3 isogenies, and they form one perfect cycle. Now, it's possible that there are a couple of disjoint cycles as well, but overall you can expect one big cycle. Let's go to the isogeny of degree 5. Same thing holds. Now it's just a different cycle, but if you would follow the red edges in the same direction, then you would see that you would traverse all the elliptic curves, so the black dots, exactly once before ending up at the starting point again. You can do the same with 7 isogenies, and so on and so on. Now, why do we want a graph for all these different type of degree isogenies in Seaside? Simple, because if you add enough of them, you end up with an expander graph, which is a graph that has rapid mixing properties in the following sense. Even though there are 23 elliptic curves represented here as black dots, it doesn't take a lot of steps in this graph to go from any elliptic curve to any other elliptic curve. So, for example, if you take at most 2 purple steps, at most 2 red steps, and at most 2 green steps, then you can end up from any elliptic curve to any other elliptic curve in this graph. So if you want to use this as a key exchange, you have to imagine instead of 23 elliptic curves, we have like 2 to the power 256 elliptic curves. We also have a bunch more prime degree isogenies. And what happens then is that Alice and Bob can turn this into a key exchange. Let's say they agree upon this elliptic curves as the public key, a starting point. Then Alice performs some random walk, a fairly short walk in the graph, and ends up somewhere uniformly at random, gives this elliptic curve to Bob. Bob does a similar path, again uniformly at random in the graph to some other point, a rather short walk. Then he has an ending point. However, the path, if Bob would start and then Alice would take the same path she did earlier, she would end up at the same curve because these paths commute. Then at the end they have the same elliptic curve and they can share this public key, this private key. Alright, so as I said, you should imagine something like 2 to the power 257 elliptic curves. This is for 128 bits of classical security, I think, these parameters. And the isogenies of prime degree will be 3, 5 up until 587. And the ground field we work over is then this specifically constructed prime. It's not super important, the underlying reason why you take this one. The thing is, if you take a prime of this form, then the isogenies of prime degree this are easy to compute. Note that also I say that we use a subset of the supersingular elliptic curves over this ground field. We'll explain that a bit more in depth later, why only a subset. And in this graph, then we will take 5 steps in either direction in the graph. And by that I mean, with the previous image in mind, at most 5 steps for every color. Notice that we have 74 primes as well, and 5 steps either way, or even 0 steps gives 11 options, and we have 74 primes. And this number pretty much equals 2 to the power 256. And there are heuristics to assume that all these random walks will end up in the huge graph of 2 to the power 257 elliptic curves, almost uniformly at random. There are a couple of collisions to be found, but you can expect this to be uniformly at random. Alright, now we're going to take a look at the supersingular isogeny volcanoes over Fp with p equals 3 mod 8. So it's a mouthful, but it's a lot of pictures coming on. Terminology of isogeny volcanoes is something from Dels and Galbraith, and terminology actually creates some nice pictures, as you'll see. First of all, we kind of need to expand our view in the following sense, that let's say we have one huge cycle, but imagine there being 2 to the power 256, denoted by these dots here, and then we're going to flatten it. So you kind of have to imagine it three-dimensional thingy here. And as I said before, we only use a subset of the supersingular elliptic curves over the ground field. More specifically, we use the supersingular elliptic curves over the ground field, which have this endomorphism ring. If you don't know what that means, it doesn't matter much. However, there's also other ones to be found. More precisely, there's a second option. There's supersingular elliptic curves with this endomorphism ring. Now, as you can see as depicted, there's less of these than the other ones. More specifically, for every one elliptic curve on this top layer here, there are 3 on the bottom. You can prove this. So actually in the C-side setting, you use most of them, since we work on something with this endomorphism ring. Now these are 2 examples of L-isogeny volcanoes. Both the top and the bottom one are volcanoes. They're just a cycle, they're very boring volcanoes because they have height 0. So their surface and their floor collapses and are equal, but we'll see some other images in a bit where you can actually see what a volcano looks like. Note that specifically I didn't note it here that this is for odd L. Let's see what happens when L is 2. Obviously we still have the same elliptic curves over the ground field, we still have elliptic curves with this endomorphism ring and this one. However, now there are no horizontal isogenies, all of them go from all of them change the endomorphism ring of our elliptic curves, and in this case we call them vertical isogenies. Note as well that these are many 2-isogeny volcanoes, because every one elliptic curve here depicts the surface of an isogeny volcano, and the 3 at the bottom depict the floor of the isogeny volcano, and every 4 tuple of elliptic curves like this forms a small isogeny volcano. Again, not the most interesting isogeny volcano, but still an isogeny volcano. Alright, now let's try and mesh these together into one picture, and then we end up with this. Again, we have the same elliptic curves and the isogenies as well. The only thing that's kind of weird now, or not immediately obvious, is maybe what happens on the floor here. Remember that I said you could decompose isogenies. So if you have a 2L isogeny, you could either do an L isogeny first followed by 2 isogeny, or a 2 isogeny first followed by an L isogeny. So let's say you start here, do an L isogeny first, then go down, then you end up somewhere here. This should correspond with an 2 isogeny first, and then an L isogeny followed by that. That's why this cycle on the floor, which is still a cycle by the way, is now a cycle that's spun around 3 times to make the picture actually work out, because the isogenies still have to commute. If you do a horizontal L isogeny, then a vertical 2 isogeny should be the same as one of the other 2 isogenies followed by an L isogeny. So now we just have a cycle that spins around 3 times. Now as you can see, we work on the floor, and this is just a picture for one L isogeny. In C-side we have 74 different L-isogenies creating this expounder graph, as said before. However, we can't really add 2 as a prime to implement 2 isogenies because 2 doesn't expound anything. It just translates or maps the problem from the isogeny problem on the floor to the surface, or maybe back, but you can do as many as you like. You're not gonna do any rapid mixing with this. So 2 isogenies in the C-side setting as is kind of useless. Okay, we're gonna try and put some change into this. We're gonna look at the supersingular isogeny volcanoes over FP with P equals to 7 mod 8 this time. Not a lot different from the title, but still rather different from what will happen. Okay, first picture. Again, we have two possible endomorphism rings. We still have surface and a floor. Again, we have 2 in the case of odd L-isogenies. We have 2 disjoint L-isogeny volcanoes. Again, boring volcanoes, depth 0, so they're just like a crater, which is exactly their cycle. But as you can see now, which is different already, is that they have the same size. Indeed, you can prove that there's the same amount of supersingular elliptic curves over FP with this endomorphism ring as there are with this endomorphism ring. So that's a small first difference already. However, the 2 isogeny behave wildly different here when P is equivalent to 7 mod 8. As you can see here, this is a picture of an actual volcano, a proper one with a nice crater at the surface, and then the vertical isogenies go to the floor, but there are no horizontal 2 isogenies on the floor. Okay, this is a proper volcano. Let's see if we can mesh this with the L isogenies for alt L in a nice picture again. This doesn't really work. You can't really make a nice picture out of this. Why not? For the simple reason that on the surface, the 2 isogenies now behave just like regular odd isogenies. They form one big cycle. So if you want to add another L isogeny graph into your picture, it should be one big cycle as well, of size about 2 to the power 256 if we're in the C-side 512 parameter setting. So it's kind of hard to depict this. But this is great. Why? Because now we can use 2 as an arbitrary prime. We had 74 prime degrees that we can use before, and now we have 75. We have an extra prime, which is great because you can't really fit in an infinite amount of easy to compute prime degree isogenies, but now we have 1 extra. So we have sped up the C-side setting a little bit already. However, 2 isogenies behave very differently in a sense by ways of computing them as well, and we'll see how this works right now. First of all, a 2 isogeny can be identified through the non-trivial 2 torsion points in the kernel. This is, if you don't really know what this means, it doesn't matter much. It's just that a 2 isogeny is 1-to-1 with some 2 torsion points, and a 2 torsion point is basically taking the equation of the elliptic curve, evaluating y at 0, and then solving it for x. We have a cubic equation, x equals 0 is obviously a solution to that, and then we're left to find the roots of some quadratic equation, which is, well, high school mathematics, basically, and we end up with these 3 2 torsion points. Okay, let's focus on these 3 2 torsion points a bit. First of all, we're taking a square root, but we're working over a finite field, so we really need to think about what are we doing here? Do we have to go to a field extension, or are these in FP? Well, by simple construction, these are in FP. Why? Because we assumed we are on the surface of the 2 isogeny volcano, and we have 3 rational outgoing 2 isogenies. That means that also the 2 torsion points are rational. So that's a check mark already. Another question that we should ask is, which square root? Because over FP it's not really obvious. If you have a square root, which one is the plus, which one is the minus? Can you distinguish in a canonical way? The answer to that is yes, and it's very easy and in a way very natural. You can take the square root of alpha over FP with P 7 mod 8 as being exponentiation to the power P plus 1 over 4. Obviously the other root will be minus alpha to the P plus 1 over 4. But why should you take this one as the positive or canonical one? Because this is a square again. You can take the square root of this and then you just end up with alpha to the power of p plus 1 over 8. And if you take this as the canonical one, which we use a lot in proving all our lemmas in our paper, then you can see that this in a sense is the correct one, or the obvious one at least. Alright, from these two torsion points it's also very easy to determine the explicit two isogenies. Let's say if you start from this Montgomery form of an elliptic curve, then the three two isogenous curves are as follows. The one in the middle is obviously the one corresponding to the kernel generator 0, 0. But again, as you can see, the others are very easy to obtain as well. One square root, and at most a handful of other operations such as addition, subtractions, and maybe a couple of multiplications. So that's it. So these are really easy to compute. Now we also want to know which one we will want to take, but maybe more importantly, which one we want to avoid, because remember the two isogeny volcano, we had one path going down, which doesn't really rapid mix in our supersingular elliptic curve isogeny graph. It just maps the problem from the floor to the surface and vice versa. So we kind of want to identify the ones on the surface, the horizontal two isogenies. Again, you can still do this, and it's actually rather easy. With halving a two torsion point, we mean the four torsion point that doubles to the two torsion point, of course. And this way we can actually distinguish the types of two torsion points rather easily in the following sense. There's a point P minus, of which the halves are not defined over the ground field. There's a point P1 plus that has halves that have x coordinates defined over FP, but not the y coordinates. And then there's a P2 plus that has halves that are completely defined over FP. Now let's go back to our picture. And if you would actually map this out, you can prove that P minus, so the points that have halves that are not defined over the ground field, correspond to the vertical isogenies. So we definitely want to avoid that. At every point in this isogeny graph, the vertical isogenies going down correspond to the points P minus, so the halves that are not defined over the ground field. Furthermore, the points that have halves that are completely defined over the ground field actually all go the same direction, depicted here counterclockwise, and then the other points P1 plus go the other direction. So in a way, this characterizes the two torsion points, but also the two isogenies. But we still want some sort of computation or equations, obviously. And let's say we start from the Montgomery form, the well-known Montgomery form here. Y squared is x cubed plus ax squared plus x. Now, the initial step is slightly trickier in the sense that we want to orient P minus at 0, 0. This is a translation at most, pretty easy isomorphism, so we may want to do a little bit of arithmetic to change this form into a same form but with a different a. But when you do that, then you can see that P1 plus will always be the one with the negative square root two torsion point, and P2 plus will always be the one with the positive square root. Okay, let's say we perform the two isogeny with kernel P2 plus, and what we'll do then we'll end up at some new elliptic curve, E prime, again assume a Montgomery coefficient A prime. And now P1 plus prime, so going back, corresponds with two torsion points 0, 0. Note that we do not want to go back. Why not? Because from a rapid mixing point of view, going one step forward and then one step backwards doesn't really do anything, so at no point we want that, so we don't want this one. We still don't want to go down ever, really, because this doesn't do much from a security point of view. It's just computation that don't really matter much. And this time, the negative square root corresponds to P minus. So again, going forward in our two isogeny walk, we need to take the positive square root, which is again corresponds to P2 plus prime this time. But this is great, and this is true for all the subsequent steps. So if we want to go counterclockwise in our two isogeny graph, all we need to do is quotient out this point, the isogeny with kernel generated this point over and over and over again. Again, the explicit iterative formula is like this, starting from a Montgomery coefficient A, quotienting out this subgroup, we end up with this new coefficient, label this one A prime, and then we go back and repeat this process over and over. Now, as you can see, this is a very easy formula, one square root and a couple of other arithmetic operations in FP, but that's about it really. Remember now that the square root extraction was basically one exponentiation. Pretty easy. And if you do square and multiply, this is 1.5 log p multiplications. Now, in a way, I wanted to take the slide here to compare this to an L-isogeny and how hard it is to compute an L-isogeny, but there's a lot of subtleties there. For example, if L is really small, let's say L3, you can find the root of the modular polynomial of degree L. However, in the C-side setting, you still sort of have to determine the twist. If you don't know what it is, it doesn't matter. For medium to large L, you also have to generate an L torsion point and then compute the image curve on top of that, which, depending on how large L is, may be done in either O of L operations or O of square root L operations. But as the footnote says, it's a lot more subtle in the C-side setting. So in a way, it's kind of hard to compare the computational cost of a 2-isogeny with an odd L-isogeny. But still, overall, a 2-isogeny, as you can see, is at least on the efficient side of L-isogeny computations and will beat a lot of them straight up in a one-to-one comparison. So with this in mind, we kind of have to propose different parameters because C-side was implemented with a P that was 3 mod 8. We now suggest using this P, which is 7 mod 8. This allows us to use the 75 different primes listed here. And again, there are roughly 2 to the power 256 elliptic curves for classical security of 128 bits, if I'm not mistaken. Alright, the difference now is that previously we took 5 steps at most for every isogeny degree, but now we're going to either use 4 or 5 steps for the odd primes. And for the 2 isogenies, because they're so efficient, we noticed that it was optimal to take a lot more precisely 137 at most. Obviously, you can take any number from minus 137 to 137. But just because they are mainly dominated by an exponentiation as computational cost, you can and should take a lot more of them. And you can remark that now we have 46 prime degrees where you go from minus 5 to 5, 28 prime degrees where you go from minus 4 to plus 4 steps, and then the 2 isogenies we have 275 options ranging from minus 137 to 137. And again, this is roughly 2 to 256, and heuristically, you can end up at any random, uniformly random at any supersingular elliptic curve in our graph. Alright, so in conclusion, our contributions to this was to change the C-side setting to P equivalent to 7 mod 8, which allows the use of horizontal 2 isogenies. Moreover, we've proven that the 2 isogenies have formulas that are easily iterable and very explicit. And this resulted in a speedup of about 6% over the classical C-side 512 parameters. It should be noted, however, that if you go to the higher security levels, so more than 128 bits of classical security, that the speedup would lessen because the impact of an additional prime to those parameters will be lower. And as future work, I would like to mention something that we've been working on as well. That is Wouter Castryck, Frederik Verkouteren, and myself, which are radical isogenies. It should be on ePrint soon, or already there, where we prove that similar explicit iterable formulas exist for higher degree isogenies too. So just taking the square root will generalize to nth roots, and the formulas are very similar in complexity and can also speed up C-side as well.